Hello everybody, today we're going to do part 1 of our periodic trends PowerPoint. We are going to break it into 2 parts because it's a little bit longer than normal. So I like to start this with a little bit of a warning, some tips, some suggestions. This chapter does tend to be a little bit harder for people. There's not as much math to fall back on. There's a lot more pattern recognition, and you do have to do a little bit more memorizing of some of the explanations and make sure that you're using correct terms and giving really good, thorough written answers. So one of the things that makes this hard for people is that they way overthink it. You do not want to talk yourself and rationalize yourself into backwards answers. So what I suggest you do is really focus on the fact that we are only going to learn a couple of trends. You got to practice those trends over and over and over. You do not want to be elaborating too much. The more you keep talking, the more you keep writing, the more likely you are to say something wrong. So be very careful, okay? Last thing that really bothers people is there's always a lot of exceptions. You have to understand, I'm going to say this all year long, high school level chemistry is focusing on the patterns. If we can understand the basic concepts well enough to explain and follow a pattern, that means we know a lot. So do not get all hung up and frustrated and upset about exceptions. I will tell you right now, if you Google some of the answers on your homework, you are going to get wrong answers, okay? Everything I ask you to do is based on the patterns. So if you Google an answer and it's a weird element and it's a bizarre exception, I'm not giving you credit for Googling an answer, okay? We are seeing if you can follow a pattern that I taught you. So just keep that in mind. So when we're doing our notes, when you're giving answers on worksheets and quizzes and tests, you need to focus on 3 pieces. What is the trend? How does the trend show up on the periodic table? Which direction is it changing? And why? That's what we need to focus on. What is the trend? How is it changing? And why is it changing? So part 1, we're going to start with atomic radius. Atomic radius is not something that can be easily measured. An orbital does not have a tangible edge. We cannot measure from the nucleus to the end of an atom because it doesn't have a hard, tangible edge. Remember that orbitals are just a mathematical, statistical probability of where we think we might find an electron. So I can't really know where to stop measuring. So the classic way to do this is to bond 2 atoms together, and then you measure between the 2 nuclei because those are tangible objects, and you cut it in half. Is that perfect? No. Are there other ways to do this? Yes, but this is the classic way. This is the way they like us to teach you because it does really show the concept that orbitals are not tangible, so we have to be more creative. So we can all probably guess that the radius is going to get bigger as we go down the periodic table. However, it is a little bit strange that it is going to get bigger as we go to the left. And that doesn't quite make sense. People say, but wait a minute, if I go from, example, element 19 to 20 to 21 to 22, as I go to the right, I'm going to be adding protons, I'm adding electrons, I'm adding neutrons, I'm getting heavier, and you're telling me that the radius gets smaller. And yes, that's true. It is very counterintuitive, and we'll figure out why. So for our trend, it goes down to get bigger, and going left gets bigger. I like to be lazy and just draw one big arrow going diagonal across the table. The head of the arrow will always point in the direction of getting larger. So increasing down is a fairly straightforward answer. We're adding energy levels. However, if you stop there, that's kind of the equivalent of a middle school level answer, right? You got to give me more than that. Why would adding energy levels mean that it gets bigger? Well, when you add energy levels, they're further from the nucleus, so it gets bigger. That's better, but not quite, okay? If you want all of your points, full credit answer, you got to explain these two pieces, but you got to add this extra bit. What we have to include is the concept that the nucleus and the electrons have an attraction. One is positive, one is negative. There's an electrostatic attraction. And if you keep adding more energy levels, more shells of electrons, what's going to start happening is the inside electrons are going to start acting like a shield, like a buffer. They're going to kind of dampen and hide and lower the attraction between the nucleus and the valence outside electrons. So the more levels of electrons you have, the more shells you have on the inside, the more weak the connection is, the attraction between the protons and that valence outside electron. And they're going to end up with all these repulsions between electrons happening, and you end up with this, less force tugging them together, and so you end up with a bigger atom. It's going to be easier for us to explain why the radius decreases going to the right. So I know that feels tricky, that, most of the time we talk about why do things get bigger. Well, this time it's going to be easier to explain why things get smaller. So let's just go with it. So we're adding a proton, we're adding an electron, but what you have to understand is that is not an equal addition of strength. Adding a proton is a bigger change than adding an electron. The analogy that I like is if you were playing tug-of-war and you had a 5-year-old on one side and a giant professional football player on the other side, that's not an equal addition of strength. If I add another 5-year-old and I add another football player, I'm adding one person to each side, but I am not adding an equal amount of force. And so that's what's happening here. So the more protons you add, the harder they can pull in those valence electrons. And if they're pulling harder, they're pulling them closer, your radius gets smaller. The way we kind of capture that concept is with the phrase greater effective nuclear charge. And that means that the nucleus is going to have a stronger effect than that extra little tiny electron that you added. So if you look at potassium and calcium, for example, number 19 to 20, yes, calcium has more protons. Yes, it has more neutrons. Yes, it has more electrons. Yes, it's heavier, but it has a smaller radius. The extra proton is pulling in that 4s2 electrons, right, a little bit harder than you would expect. One thing that's important to understand is that when we're talking about a left to right change, we are not adding any shielding, okay? There are no new energy levels that are being added. If you're in row 3, as you go across, you're staying in row 3, okay? So you have to make sure that you kind of keep straight the fact that when we're talking about going up and down, we're talking about shielding. When we're talking about going left to right, we're talking about effective nuclear charge. I love this diagram. Okay, what this diagram is showing you in blue is the effective nuclear charge concept, that the nucleus is trying to pull in these electrons. Nucleus is positive, electrons are negative. This electrostatic attraction is trying to pull it closer together. They want to be next to each other. In red, you can see the effect of the shielding. All these inside electrons are repelling these outside electrons, and they're kind of causing this buffer, this shield, so that the poor nucleus cannot pull as hard, and so they would end up a little bit further out than normal. I love this drawing too. This little cartoon. We have our valence electrons out here on the outside, and our nucleus has a effective charge and is trying to pull them in, and all these inner electrons are acting as the shield, as the buffer, and so it makes it so that the nucleus cannot pull them in as close as it would otherwise. We can do this mathematically. We can calculate the effective nuclear charge. The problem is it gets very complicated very fast, and what we're going to teach you is a very, very big oversimplification. If you are going to start looking this up online, you're going to start seeing things called Slater rules, and they're horrible. You don't want to have to do it. So just let it stop at this simplification, okay? So what we're going to do is we're going to be calculating the effective charge by subtracting. We're going to do Z minus S. Z is the number of protons. S is the number of inside core electrons, okay? And what you're going to do is you're going to figure out how many of your total electrons are the inside ones, which ones are not the valence electrons. Some people like to think of this as counting up your total number and subtracting out the highest S&P levels that you have. The way I like to do it is I like to look at the previous noble gas, because that's all going to be inside electrons. That's why we learned noble gas configuration, right? Those are all core electrons, inside electrons. And then we also just have to make sure that we take a look and make sure there's no D and F electrons to throw in there also. And then that will give us our inside total electrons. So let's do an example. Magnesium has 12 protons. The previous noble gas would be neon. So even though there's 12 electrons, only 10 of them are actual core electrons. Magnesium has 2 valence electrons. The 3s1 electron and the 3s2 electron are valence. They're on the outside energy level, okay? So if I want to find out what the effective charge is I'm going to subtract out the ones that are shielding. And that's going to tell me that my effective nuclear charge is 2. It's just kind of this arbitrary number. It doesn't really mean much until you compare it to a different element. So let's compare it to aluminum. Aluminum has 13 protons. Aluminum also has 10 inside core electrons. It has 3 valence electrons on the outside, okay? So if I do 13 minus 10, I find out that aluminum has a Zeph of 3. Now what I can do is I can compare these to each other. So when I compare them, I'm going to find out that aluminum ends up smaller. Because if aluminum effectively has a stronger nucleus, aluminum can pull the valence electrons in closer than magnesium can, which shrinks that radius down. So even though aluminum is heavier, it has a smaller radius than magnesium does. So looking at your Zeph is a nice simple way of saying, yeah, okay, aluminum will be a little bit smaller. You cannot use a Zeph calculation as your only explanation as to why something is bigger or smaller. You do need to explain the concept of effective nuclear charge. You can't just throw out a number and say Z equals 3, right? So be a little bit careful that you don't rely on this as your only piece of explaining, okay? All right, let's move on. Let's look at ionic radius. Okay, well, it's the radius of an ion. Remember, a cation loses electrons and an anion gains electrons. This time the pattern is going to be that cations are always smaller and that anions are always bigger. A cation is always going to be smaller because if you take an electron away, you're going to have reduced repulsions. which means they're not going to be pushed out as far, so it'll end up with a smaller radius. If you keep taking electrons away, pretty soon you're going to drop down to a brand new energy level, which is going to be way smaller. So a cation, depending on how many electrons you take, can end up significantly smaller than the neutral version of the atom. An anion is going to be larger because you're going to get extra repulsions. So once again, our explaining needs to go beyond you lost an electron, you gained an electron. You need to explain this attractive force or this repulsion, right? All of our answers are going to kind of come back to the attractions or the repulsions. When we start looking at ionic radius, we need to start asking ourselves, how does the repulsion change? And that will change our radius. I love this set of examples because I think this really shows the fact that the nucleus is powerful, okay? Most of chemistry is all about the electrons. That's what makes our bonds. That's what we always look at. That's what we're always drawing. But the nucleus does matter, okay? So everything you see on this screen has the same number of electrons. Everything here has the configuration of 1s2, 2s2, 2p6. They all have 10 electrons, but they are not all the same size. The number of protons are going to affect the radius. So we're comparing 10 electrons in every case, but as we go from oxygen to fluorine to neon to sodium to magnesium, we're adding in a proton every time, aren't we? So our effective nuclear charge is getting bigger and bigger and bigger. Our nucleus is pulling the electrons in tighter and tighter and tighter and tighter. So you're going to get these atoms or these ions that have a different radius than you might expect if all you were doing was counting the number of particles. We can't just count the objects. We have to think about how the objects interact with each other. It's not just about how many protons and how many electrons. It's about how do the protons and electrons interact with each other. Right? So you can see here, we get way more. So the increased protons pulls in those valence electrons. All right, ionization energy. This is exactly what it sounds like. This is the energy that is required to take away an electron to turn it into an ion, okay? It is always framed from the perspective of removing an electron, okay? We have a neutral atom, we're going to remove the electron. It's going to increase as we go up. It's going to increase as we go to the right. I like to be lazy and draw a big diagonal line. One of the things we need to be careful of is that the noble gases are going to kind of be their own separate column. They are so much higher than the rest. They are so perfect. They love their configurations. They are super stable. They do not want to get rid of an electron. They do not want to make things worse for themselves. So they're going to kind of be their own standalone column. When we draw our arrows, right, we have to really make sure that our brains remember that those noble gases are extra, extra high compared to the rest. I love this little cartoon. If we have high ionization energy, it really wants to hold on to its electrons. It doesn't want to let go of them. It's going to pull on them really tight. Low ionization energy, it's like, whatever, I don't care. You can take my electrons. Now, it takes a little bit of energy to remove them. They don't just go flying off by themselves. You do have to put a little bit of energy in, but it's not nearly as much as something that has a high ionization energy. So, as the electrons get further from your nucleus, they're in higher energy levels. You have increased shielding, right? The shielding is causing the protons to not pull as hard on the electrons, which is going to make it easier for them to come off, isn't it? So as you go down, it gets a little bit easier. Now, going to the right, okay, you're closer and closer to having a nice stable valence shell. The closer you are to a stable valence shell, the less likely it is to be able to take an electron away. You have an increased effective nuclear charge. Your nucleus is pulling harder on the valence electrons, so they're harder to remove. Because that radius was smaller, right? That's why we had a higher effective nuclear charge. So you can see once again, our answer up and down is about shielding, and our answer left to right is about how strong is that nucleus. And that's a pattern that tends to repeat. One thing to keep in mind is that you can take more than one electron away. So if you look at sodium, our first ionization energy is 496. I have to put in this amount of energy to take an electron away. And then if I want to take a second electron away, it jumps a huge amount. I mean, this is like times 10, right? You have to pull really hard to get a second electron away. And that's because sodium, if it loses an electron, instead of 11 electrons, it now has 10. And now it looks like neon. If it looks like neon, it does not want to let you take another electron away. So in order to go from 10 electrons to 9, look how much harder you have to work. Losing one electron for sodium has stabilized it, and it does not want to let you go again. Whereas magnesium, you take one electron away. The second one's a little bit harder, sure. You got to work a little bit harder because there's less repulsions, and now the nucleus is pulling harder on the last valence electron. So you got to put in a little more energy. But look what happens when you try to take the third one away. It jumps like crazy. That's because after you've lost the first and second electron, now magnesium looks like neon and it's extra stable. It looks like a noble gas. Taking a third electron is going to make it even worse. It does not want to do that. If you look at aluminum, okay, I put in a little bit of energy. Okay, it's a little bit more to take the second one. It's a little bit more to take the third one. But oh my gosh, look at the big jump here. Taking that fourth electron away is crazy. Okay, that's going to take so much energy. Because if you take away the first three, it looks like a noble gas. It's not going to want to get worse than that. Okay, it's not going to want to make a worse off, less stable situation. You can look at a chart like this and you can figure out what the charge is likely to be by finding where you have this giant leap. When I look at this chart and I see, okay, kind of like doubled, oh my gosh, look at that. Huge jump. Well, that's telling me this is probably going to be a +3 ion. When I look at this one, okay, kind of, doubled, and then, oh my gosh, it went all the way up to 7,000. Okay, that's probably going to be a +2 ion, because the first two were relatively easy. The next one was crazy big jump. When I look at sodium, I'm going from here times 10. Okay, that's definitely a +1 ion. So you can use these subsequent ionizations to kind of justify and predict what you think the charge would be. All right, that's going to be it for part 1. That feels like a lot. We kind of only did 2 trends. We did the radius and we did the ionization energy. What I'm going to ask you to do is I'm going to ask you to go over this, reread the notes, rewatch the video, practice these, explanations over and over. Ask me to explain it over and over. We can draw pictures of it. Really, really practice the first part. And then the next day, what we'll do is we'll do part 2. Okay? All right, everybody. That's it. Bye.